Hello, everyone. In this lecture, we're going to talk about statistical learning. The outline of this lecture, we're going to talk about what is statistical learning and what is the difference between statistical learning and machine learning, and why estimate the model and how to estimate the model. And also, what's the difference between supervised learning and unsupervised learning? What's the difference between regression and classification? In the end, if we have a model, we want to evaluate and assess the model accuracy. What is the quality of fit, bias, variance, trade-off, and also the classification performance. Now let's first have a look at the difference between statistical learning and machine learning. So statistical is statistical. You see the keywords is statistical. So it emphasizes the data understanding, while machine learning emphasizes the machine, right? The adjective is machine. We want to make the machine learn something, right? So computer learning, and which is a subfield of AI. Statistical learning, we emphasize the data, which is a subfield of statistics and IE. But they overlap. Sometimes people use them interchangeably, but I want you guys to have a better understanding of statistical learning and machine learning, and what are the differences. So statistical learning emphasizes the models, interpretability, and prediction and uncertainty in the model. Computer science focuses more on the large-scale application and prediction accuracy, but there are some cross-fertilization. So for example, statistics, OR, robotics, control, and marketing, computer science, and automation. So people know more about AI and machine learning. That's because computer science right now, they advertise the AI and catch a lot of eyeballs in the news. So people know more about AI. But I just want you guys to understand the statistical learning, which is sometimes AI borrow ideas and the concepts from statistics, from IE and the optimization, and the IE and optimization sometimes they have also borrowed ideas from computing and the AI, right? So this is called cross-fertilization or interdisciplinary field, okay, or multidisciplinary field. Now let's have a look at an example of the statistical learning. So you see a bunch of scatter plot. So for any plot, let's have a look at what is the X label and the Y label. So here, the X label is TV, as you can see here, TV, radio, and newspaper. So those are all you predictors or input variables. So input variables, we often use X, right? So you have X1, this TV advertisement, and how much money did you invest in the TV advertisement? And or how many advertisements have you put out in the TV, right? X2 is radio, and X3 is newspaper. So what we want to do is, can we predict sales using those three predictors? So you have TV, radio, and newspaper. Can we predict sales based on the advertisement, how effective they are? So the response variable, or we call it output variable, sometimes we use Y to denote the response variable. And so we need a model. So these are just data. We haven't built any model yet, but what we really want is, we want to build this model to predict the sales. And so the first question is, are these three predictors or input variables, are they associated or related to, are they relevant to the Y, the response variable? And if they are relevant, then can we predict sales using the variables? Second question. And if you can predict, then can we instruct? Third question is, can you instruct clients on the advertising strategies? For example, based on the budget, how do you allocate the funding to boost your sales? So those are this is a problem that we are trying to study from the data. So in order to study this problem, obviously we have a very good business opportunity or business objective. But in order to do that, we need to understand the mathematics and the models behind the analytics, So let's first have a look at the notations. So we use, as we just discussed, we use Y to denote a response variable. And sometimes people call response variable as a target or output variable or dependent variable. And X, sometimes people call it predictor, features, or input variable, or independent variable. So people use those words interchangeably depending on the context and the scenario. So I want you guys to understand the real meaning of those X and Y, not just get confused by the names. So there's 3X: TV, radio, and newspaper. So each X, so you see here X is capitalized, but we have this lowercase one, and this denotes TV, radio, or XP. So here we have X3, that's newspaper. Now we can establish the model as Y equals to Fx plus epsilon. So what is epsilon? Epsilon is the measurement errors, or you can call it discrepancies, because models sometimes they can capture some relationship, but there are noise or errors in the real world. So if you have case one, he got a particular sales achievement based on TV or different kind of advertisement in TV, radio, or newspaper. And then you got a product two, you use a different, and then you have N. So in total, you have N is a number of observations. So here, this Y response variable, you have one sample, right? This is one sample. And in total, you have N observations, okay, of the samples. And a P is the dimensionality of your predictor variable. So you have for the sample one, you have Y1, X11. For sample one, you have the first predictor. Sample one, you have the second predictor. And sample one, you have the P predictor. Sometimes you have three predictors. Sometimes you have maybe 10 predictors. Sometimes you have hundreds of predictors. So, but you want to organize the data in this way. You want to differentiate what is your P, what is your N, right? And how are they corresponding to each other? For example, this row, and this row. They are actually one-to-one correspondence, right? Now, if we have, for example, the P this P could be, this is N by P matrix. Okay. Sometimes you may only have one predictor. This is called simple linear regression. Sometimes you have many predictors. So let's have a look at a simple regression. That means you only have one predictor. This is one predictor, right? And then you have one response, but you have different observations. That means each observation is 1 point. So this is you have X1, Y1, right? So this is your X1, Y1. And then what we want to do is to, for example, this is years of education, and this is income. And you want to make some prediction. So Y equals to Fx plus epsilon. So this F, you see, we don't have a hat. This is called true model. And then this epsilon is called errors. And if you put a hat, then you have epsilon hat too. And then you have your predictions. That means this is your estimated model, or this is your prediction model, because this model is estimated from data. It may not be the same as the true model. So you see, one has a hat, the other doesn't have the hat. So that's a difference. And this is estimated model, right? And this we use the blue line. The estimated model, you have x1, y1 hat, x2, y2 hat. Because why do we put a hat? Because these are predictions; they are not the true values. Because predictions, for example, this is y1, but this is predicted by the model y1 hat. Okay, y1 hat, yeah. And the discrepancy is called residues. But you might have a true model. The true model maybe look like this, right? This is a true model. Then true models still have discrepancies. These are called errors. If you want to understand what is the difference between errors and residues, please refer to the video. We have a video specifically on the population sample and the errors and the residues. I hope you guys to check the details in that video. So in simple, in the layman term, residues are the estimated model and the discrepancy from the estimated model to the observation, right? To the data point. And the errors are actually the true model. Sometimes you don't know the true model. You can only estimate a model from the data. Errors are the discrepancy between true model and the data observation. That's a major difference. So far we discussed the notations we're going to use in the, for example, here. Go to the previous slide. Okay, go to the previous slide. Okay. So those are the notations we used, and those are some terminology that we used in the modeling and a data format. Now, why do we estimate the model? Because if you estimate the model, you can do the prediction. So this is a true model, and this is if you have epsilon doesn't have a hat, so this is an arrow. But the arrow is sometimes irreducible. Even if you know the true model, we would still make errors in prediction. Since at each x, there is typically a distribution of possible y values. So we estimate the model. These are the true model. This is the estimate model. We have a hat. In the estimated model, we will have reducible errors, because the true model and the estimate model, they have errors, but this error is actually reducible if you improve your model, try to make it close to the true model. But the variance is actually irreducible. The variance of the epsilon, the errors, these are irreducible. Inference means if you know the model and you can see, you can make statistical inference. For example, those questions like which predictors are associated with the response? What is the relationship between the response and each predictor? Can this relationship be adequately summarized using a linear model or a more complicated model? So for the advertising case, obviously we want to answer those questions so that we can have better advertisement strategy. So if you formulate the model, if you have a hypothesis, I'm going to use a regression model. Then how do you estimate the model? You see, we have training data. So training data is all the data you have. You have all the response variables, and you also have M by P predictor matrix. Now you have there will be an unknown true model, and what you are trying to do is estimate the model. And the observation and the estimate model, the discrepancy, we call it residues. So we can do the parametric modeling. Parametric modeling means f is linear in x. So fx equals to beta 0 plus beta 1, x1 plus beta 2, x2 plus, and until you go for beta p, xp. So in total, how many coefficients you have? You see, we start from 0 and beta 1, beta 2 to beta p. So those are the parameters, p plus 1 coefficient. Those are the parameters. You want to estimate those parameters. So this is called parametric modeling. In order to estimate the parameters, obviously you want to find the best set of parameters or optimal set of parameters so that you can minimize the ISS. ISS means residue sum of squares. You see, you have all the residues, and in total you have n observations. So you want to sum them up, but let me go to the previous one. You want to residue sum of squares. That means you got a residue, and then you got a square, and then the sum. So this is called residue sum of the squares. So ISS, residue sum of squares. Non-parametric, you can do parametric or you can do non-parametric. Non-parametric is k nearest neighbors, and we're going to get into details in the next few slides. So parametric modeling, we have a model xi, yi hat in this line, and then you have these data points. These data points are x, I, yi. Okay, and then you have discrepancy between this yi hat and this yi. So this is called residues. And you see, this is a true model. Yi equals to fxi plus epsilon. So this beta doesn't have a hat. But those true model, you don't know. This is a true model which generated the data. You don't know. And then you only have xi, yi available. You only have the data available to you. And then based on the data, you estimate the beta 0 hat and the beta 1 hat, and then you generate a prediction. And the prediction has discrepancy from the data. So this is called residues. This is a simple linear regression, but if you look at the multiple linear regression, this is fitting a line, right? And in the right-hand side, you are fitting a hyperplane. So in 3-dimensional space, you are fitting a 2-dimensional plane, right? And but you can go to 10-dimensional higher dimension. It's a hyperplane. And same thing, you will have data available, right? And then you will have predictions. You will have predictions. These are the predictions. Okay. Based on X, you want to predict the Y, and this is the data. And then you have discrepancy. The discrepancy is epsilon I hat. So non-parametric modeling, for example, if you have X, right? And if you know where your X is, and then you find a neighbor of your X, so you find the neighbors. And then Nx is a neighbor of X, and then you find all the Y, and then you average all the Y, then you got the prediction. This is called non-parametric modeling. Okay. And the k-nearest neighbor. K-nearest neighbor means if you are here, right? If you 3 neighbors, then you find this neighbor, and this neighbor, then you find the Y, then you average Y. Because for x0, you want to find the neighbors, and then you find the values of all the neighbors, the response variable of all the neighbors, and then you do an average. Yi equals to j, right? Then you have, so a test observation, x0, and then identify k points close to x0. So you draw a neighborhood. You have x1, x2, x3. Then xi belongs to the neighborhood. You have k nearest neighbors. Then you estimate the conditional probability given this, and what's the probability y equals to j, right? So this is a k nearest neighbor. And those are the boundary. You see, if you have, those are the classification problems. You have points, they are blue, and you have yellow ones. And then based on the k nearest neighbor, you can draw the boundary for the classification. So, but sometimes people may have a question like, if you are going to do the k nearest neighbor. Should we do k equals to 1 or k equals to 100? So if you only take 1, that means you have high variance, no bias, because you have too few neighbors to average. And then the error rate, you see error rate is 0.1695. And but if you take too many neighbors, it's much smoother, right? Yeah, you see the purple line is actually the true boundary. And if you take too many labels, you see this black line. It's very smooth because you take too many labels based on the central limit theorem, and you are reducing the variance. So you have no variance, but you have higher bias in the prediction results. So if you wanna understand why, if we take more neighbors, the variance got reduced, please check out the video on central limit theorem, which is also available in the canvas. So this is k equals to 1. So you have high variance. You see the boundary is actually you have a big variance. So that's why you want to do a trade-off, not too many or not too few, and so that you have a good model. Then how do you do that? And we're going to talk about it. But now let's first have a look at the unsupervised learning and the supervised learning. So unsupervised learning, you have no outcome variables. That means no response variable, just a set of predictors measured based on a set of samples. Objective is to find groups of samples that behave similarly and which is different from supervised. So unsupervised, you have inputs, but you don't have, you see here, you don't have target, you don't have response variable. You only have all the X, right? And you have X1, X2, and you want to find out all the groups. Okay. N is the number of observations or number of samples, as we discussed before. Now P is the number of variables, number of predictors you have, but you don't have Y anymore. You want to find a structure in the X variable. Supervised learning is we have outcome variables. You can see you have output, you have response, you have target, or you have dependent variable. And you also have predictors. That means you have input, independent variable, features, or regressors, or covariates. These are all different names for predictor. You can do the regression. Regression is regression is a quantitative or continuous variable. And then based on the income, price, blood pressure, you want to predict, right? And classification is a discrete. So this Y, if Y is continuous, you use regression. If Y is discrete, then you use classification. That means it's a binary problem. It's a healthy or diseased, or true or false, or in this category or not in this category. Or you can have multiple class. For example, you have several characters. If you write something, which one is this? This is a classification because they are all discrete. They are a finite set. Either you have, the finite set means either you have 2 or you have multiple discrete outcomes. Survived or died, cancer classes. The training variable, the training data is always XY pairs. So supervised learning, you have examples. So each row is an example or instance or observation or sample. You have input and you have target, X and Y. Now, this is a poll, and I used to do this in my class. I ask you guys, okay, what's the primary difference between supervised and unsupervised classification? Is whether a dependent or target variable is known. Is this true or not? Yes, this is true because it really, depending on supervised or unsupervised, is whether you know the Y, you know the response variable. Now, if you build the model, how do you assess the model accuracy? Obviously, we talk about the residue sum of squares because you want to sum all the residues together, and all the residue, then you take the square, and then you sum them up. So this measures quality of the fit or the goodness of fit. goodness of fit. Goodness of fit, people have a GOF, okay? Goodness of fit. And if you average this residual sum square, it will become MSE. MSE is a mean square error. People call it error, right? So you just take the average. Here is the sum, but you didn't take the average. You take the average, okay, divided by n. You got the average. So training data, you have training MSE. Testing data, you have testing MSE. So this is denotes training. This denotes testing. So MSE, and you just divide by n. So this I belongs to the training data set. This I belongs to the testing data set. So model complexity, you see, you have this data. You may have very flexible model. That means this model is a little bit, if the model is flexible, now you have a complex model. You also have not flexible enough model. This is a very simple model. You have maybe it's just right model. Obviously, we want just right. You don't want to overfit the model. We don't want to underfit the model, right? We want something just right. So that's why we needed to split our data into, if we want to have an honest assessment, we need to do the cross-validation. Cross-validation means we need our training. We need to have we need the whole data set. You divide it into 3 groups: training, validation, and test. So the training and testing arrow, not only just the training data, the arrow that goes down, but also you need the testing data or validation. They are all going down, okay? So you don't want training data, the arrow is pretty low, but when it comes to test, it's pretty high. That means you have overfitting problems. So black curve, now you have black curve is a true model. You can do orange, blue, or green curves. These are different models, different fits of different flexibility. You see, this is orange. You haven't finished you didn't do fitting very well, but the model complexity is pretty low because you only use, what do we mean by complexity? Complexity means you use less variables or less parameters. For example, why this is a simple linear regression model, but if you go to polynomial model, you will have more parameters. If you have more parameters, this flexibility sometimes is a number of parameters. You can call it number of model parameters. If you have more parameters, then your model is more complex. For example, here, this is just right. This is less parameters. This is more parameters, okay? So these are fits of different flexibility. Then you have different mean square errors. This is MSE. So you see the model actually, this is a this is a training. The gray line is a training. This is the validation. You see, the training always goes down because this is based on the data that you gave me. I trained them, and I can go through every line, right? But when I give you some new data points, the arrow actually goes up. Okay, so you want to be here. Both of them are low, so you get this is just right model. This is another example. You have black lines. The truth is very smooth. Then you have smoother fit. Okay, even if a simple model can do, right? And then this is just right model, and this is complicated model. Actually, give you, if you have a complicated model, your MSE is actually higher. It doesn't mean that a complex model are actually better. You want a parsimonious, or you can say you want a simple model that can explain the mechanisms of your data or the physics of your data. So similarly here, the truth is actually weakly, so you need a complicated model. Okay, if the data is complicated, you need a complicated model. If, for example, the previous one, the data is not that complicated, you don't need a complicated model. And here the data is it's not that complicated model, right in the middle. So you don't want a too complex model. You don't want a too simple model. So the truth is weakly, the noise is no, right? So the more flexible fits actually do the best. So when we are evaluating the model performance, right, we feed the model to a training data. And then for new X0 in the testing data, we want to find out testing performance, right? The testing performance are composed of 3 components. The first one is called the variance of the prediction. Second one is called bias of the prediction. And then you have the variance of the errors. Okay. So if the model flexibility or complexity is up, the variance actually goes up, but the bias goes down. So this is called bias and a variance trade-off based on the model flexibility. Okay, just remember that you have, if the model is too complex, then your variance is going up, but the bias is low. So what we really want is a just right model. Just right model actually give us a trade-off between bias and variance. Now for classification model, how do we evaluate the performance? So let's have a look at this this diagram, right? So you have predicted class, you have actual class. So here we only have 2 class. Okay, 0, 1. So for the COVID-19, and you also have predicted it, right? If you do the COVID-19 test, you are actually you have the true status, like actual status, you are negative or positive. But the test can show you some results, but a test that sometimes can be wrong or can be not right. So if you are negative and then the test tell you are negative, this is called true negative. If you are negative but the test show you are positive, this is called false positive. If you are positive but the test show you are negative, this is called false negative. And if you are positive but the test show you are positive, then this is called true positive. Okay, so in this row, these are actual negatives, and in the row they are actual positives, right? And then you have predicted negatives and predicted positives. Now we have accuracy. What is the accuracy? Accuracy is true positive and true negative. These two, okay, these two divided by total case. This is accuracy. And error rate is false positive, false negative. These two added together divided by total case. And this is error rate. So in this case, for example, we have 100 students. Now in the 100 students, we have 40 negative and 60 positive. These are true status or actual status. But after the test, we found that there are 38 students, they are negative. And the 54, they are positive. Okay. And 2, in the group of true negative, in the group we have 38 true negatives, but 2 students, they are negative, but they are classified, they are tested as positive. And we have 54 positive students, they are actual positive, they are tested as positive. But we have 6 students, they are positive, but they are tested as negative. How many students do we have in total? Like 40 plus 60 equals to 100. And here we have 44 and 56 equals to 100. Now what is the accuracy? Accuracy is 38 plus 54 divided by 100. It's 92%. And what is the error? Error is 2 plus 6 divided by 100. This is 8%. Okay. So this is a perfect example that we can use in the COVID-19 test. Then what is the sensitivity of the test? Sensitivity of the test is actually the true positive divided by total actual positive. Okay, so true positive 54 divided by total actual positive, that's at 60, right? So 54 divided by 60, that means this group. What is the positive predicted value? Positive predicted value is the true positive divided by total predicted positive. That's 54 divided by 56. That is this row. This is positive predicted value. What is specificity? Specificity is the true negative divided by total true actual negative. total actual negative, that is this row. You have 38 plus 2, that is actual negatives 40, but we have 2 students. They are actually negative, but they are classified as positive. Now they are tested as positive. So specificity is 38 divided by 40. If we have a good testing protocol, we need specificity high. And also we need sensitivity is high. We don't just need sensitivity high and specificity is low. That's not a good test, okay? Negative predicted values is a true negative divided by total predicted negatives. In this case, is 38 divided by 44. Okay, so this is the end of this lecture, and the reading assignment, please read the chapter 2 of the textbook.